Hi, hello everyone from Institute of Aeronautical Engineering. Today we are going to discuss about 8 queens problem using backtracking. Myself, Dr. M. Purushotham Reddy, Associate Professor, Head of the Department of Information Technology. These are the course objectives of this subject, design and analysis of algorithms. This is the course outcome of the chapter backtracking. After successful completion of this course, student will be able to utilize backtracking and branch and bound techniques to deal with traceable and untraceable problems. Backtracking. Backtracking is a general algorithm for finding all solutions to some computational problem that incrementally builds candidates to the solutions and abandons each partial candidate C as soon as it determines C cannot possibly be completed to a valid solution. Backtracking is an important tool for solving constraint satisfaction problems such as crosswords, verbal arithmetic, Sudoku, and many other puzzles. It is also basis for so-called logical programming languages such as Planar and Prolog. The term backtrack was coined by American mathematician D.H. Lehmer in the 1950s. The pioneer string processing language Snowball 1962 may have been the first to provide a built-in general backtracking facility. The good example of the use of backtracking is the 8 queens puzzle that asks for all arrangements of 8 queens on a standard chessboard so that no queens attack any other. In the common backtracking approach, the partial candidates are arrangement of k queens in the first two k rows of the board, all in different rows and columns. Any partial solution that contains 2 mutually attacking queens can be abandoned, since it cannot possibly be completed to a valid solution. The 8 queens puzzle is a problem of placing 8 chess queens on 8 by 8 chessboard so that no 2 queens attack each other. Thus, a solution requires that no 2 queens share the same row, column, or diagonal. The 8 queens puzzle is an example for more general n queens problem of placing n queens on n by n chessboard, where solutions exist for all natural numbers n with exception of 1, 2, and 3. The solution possibilities are discovered only up to 23 queens. The puzzle was originally proposed in 1948 by chess player Max Basel, and over the years, many mathematicians include Gauss, who worked in this puzzle and it generalized n queens problem. These are the solution inventors. The first solution for 8 queens were provided by Franz Nack in 1850. Nack also extended the puzzle to n queens problem. In 1874, S. Gunther proposed a method of finding solutions by using determinants, and J.W.L. Glasser refined this approach. Exer Disgastra used this problem in 1972 to illustrate the power of what he called structured programming. He published a highly detailed description of the development of depth-first backtracking algorithm. So 8 queens problem. Here states any arrangement of 0 to 8 queens on the board. Initial state is 0 queens on the board. Success function, add a queen in any square. Goal to stage 8 queens on the board, none attacked. Now here we see that this is a queen. So no queen attack, no queen placed either diagonally or row wise or column wise. So like this we are arranging all this one. So we see that we are arranging all this here. So no here this is one solution for this 8 queens problem. Each recursive call attempts to place a queen in a specific column. For a given call, the state of the board from previous placements is known. Current step backtracking, if a placement within the column does not lead to a solution, the queen is removed and moved down the column. Previous step breaking, when all rows in a column have been tried, the call terminates and backtracks to the previous call. Pruning, if queen cannot be placed into column I, do not even try to place 1 onto column I plus 1, or rather backtrack to column I minus 1 and move the queen that had been placed there. Using this approach, we can reduce the number of potential solutions even more. So this is a 4 queens problem. In this 4 queens problem, first we place here queen 1, q1. Suppose we place queen 2 here or here or here or diagonally, in this diagonally. So the 2 queens here, the 2 queens are not placed there. Here the condition is no queen placed either in column wise or row wise or diagonal wise to this queen. So here this is the first queen. Here condition is no queen placed either a diagonal to this one or row wise to this one or column wise to this queen. So this one no need to place here. As per the conditions of n queens problem, not to place this queen here. Not to place here this queen here. So we place here. So now here, whenever we place here we see that this is not diagonal to this one or row wise to this one or column wise to this one. So here no queen is not there, either row wise or column wise or diagonal wise to this one. Next we see this one also not placed here. This is also in the same row is there. Suppose we place here, the diagonally they are in same row, so we are not placed here. Here also same row, you are not placed here. Here also diagonally they are in same direction, so not placed here. So place here. Next we place here. Now here we see that. Next we place here. This is this is not diagonal to this one, so place here. We place next one here. Here we see that where we place. We not place there. Here also not place there. They are diagonally. They are the 2 queens. They are in diagonally there. So these 2 queens in the same row is there. So not place here. So even though here they are in the same here we see that they are diagonally same. So here also we not place this queen. So in the same row we not place another queen. So now again come backtrack and we place in next row. Suppose we place here this queen. So no, not to place this queen here. No queen place in the same row. No queen place in the same diagonal or in the same column. So place here second queen. Now we place the third queen. This is not diagonal to these 2 queens. Just to place 4th queen where we see that one is possible or not. So not to place this queen here. So we place that queen here. This is a unique solution for this problem. Now here we see that how to do this one. Here we see that here 4 queens are there. 4 queens means 4 rows and 4 columns we get here. Suppose we place q1 here. Not to place q1 diagonally or column or row wise. So not to place q2 here or q2 here or diagonally. We place q2 here either here or here. Suppose we place q2 here. Next here q3 is not placed here. Here q3 is not placed here. Q3 is not placed here. Q3 is not placed here. There is no chance to place q3. So again come back. And we change q1 direction. Suppose we place q2 here. So q1 here, not q2, q1 here. So not place q2 here. Here in this one also not place. Diagonally here not place q2. So there is a diagonally here also not place. So here place Q2 here or here. Suppose you place Q2 here, Q3 is not placed here and also here. Q3 you place only here. Q3 place here, Q4 is not placed here, Q4 is not placed here, here diagonally here not placed. So Q4 there is no chance to place Q4. So we change this one. So again come back and change the direction of Q1. Now here we see that now Q1 placed here. Q1 placed here means we are not placed Q2 here. Here also Q2. Here also not placed Q2. Here also not placed Q2. So now we place Q2 here. Place Q2 here means in the same row we are not place any Q3. And diagonally also we are not place here. So Q3 here we place here. There is a chance there is a chance to place this Q3. So Q4 is not placed here, Q4 is not placed here, Q4 is not placed here. There is a chance to place here Q4. So now this is the unique solution for this 4 queens problem. So Q1, Q2, Q3, Q4. So here we place the queens with here in any row we place one queen only, and in any column or row wise we place only one queen. So like this we queen in this 4x4 4x4 chessboard we queen we place 4 queens in 4x4 chessboard with these conditions. That one is called as 4 queens problem. So here steps are revisited in backtracking. The steps are: place the first queen in the first upper corner of the table, save the attacked positions, move the next queen, search for a valid position. If there is a one, go to step 8. There is not a valid position for the queen, delete it, move to the previous queen, go to step 4, place it to the first valid position, save the attacked positions. If the queen processed is the last stop, otherwise go to step 3. This is 8 queen problem algorithm. For every position column on the same row, a position column is available. Place the next queen in the position column, row less than 8. Put queen row plus 1. Otherwise, success. Remove the queen from position column and then again come back. So like this, we place the queen. So this is the place algorithm. Place algorithm for 8 queens problem. The 8 queens puzzle has 92 distinct solutions. If the solutions that differ only by symmetry operations of the board are counted as one of the puzzle has 12 unique solutions. These are the some of the solutions of 8 queens problem. Now here you see that no queen is there either row wise or column wise to any queen or diagonal wise to any queen. So in each and every row or each and every column or each and every diagonal we have only one queen. So like that here this is one solution, this is another solution, this is another solution, this is another solution. These 4 solutions are the solutions of 8 queens problem. Generally we get 12 unique solutions for this 8 queens problem. So this is the table. So if one queen problem it get only one solutions, it takes less than 0 seconds. 2 queens problem 0 unique solution. 3 queens problem also 0 solutions, it takes less than 0 seconds. 4 queens problem we get 2 unique solutions, 2 total solutions 2. Among this we get only 1 unique solutions, it takes less than 0 seconds. 5 queens problem 10 solutions, among these 2 are unique solutions, it takes less than 0 seconds time. So like this 8 queens problem, here totally you get 92 solutions, among 12 are unique solutions, it also takes less than 12 seconds. So like that number of queens here, the number of solutions, total number of solutions and unique solutions, and it takes the time which you want to calculate that one. So 14 queens problem, it has total solutions is 3,65,596 solutions. Among this 45,752 are the unique solutions. It takes 0.2 seconds to find the solution. So these are also that number of queens, and also find total number of solutions, unique solutions, and it takes so much of time. That one is there here. The major advantage of the backtracking algorithm is the ability to find and count all the possible solutions rather than just one, while offering decent speed. If we go through the algorithm for 8 queens, 981 queens moves are required for the first solution alone. 16,704 moves are needed to find all 92 solutions. Given those figures, it's easy to see why the solution is best left to computers. This is the n queens place algorithm, place of k comma I. So here k means here the number of positions, I means you place the I queen in that in one place. So for j equal to 1 to k minus 1, if x of j equal to I, 2 in the same column, 2 they are in the same column or not, to check. If this condition is mapped, means they are in the same column. Or absolute of x of j minus I equal to absolute of j minus k. This shows that 2 queens they are in the same diagonal. So if these two conditions are not satisfied, if these conditions are satisfied, then return false. If these conditions are not satisfied, means we place that queen in that particular position is possible. So that's why we return here true. This is n queens algorithm. So k means number of places, n means queens. So for I equal to 1 to n, so repeating for all n queens, in place of k comma I, then so place of k comma I means we call that place k comma I algorithm. So with that algorithm, we check it in the same row or in the same column. Any queen is there, we not place that queen. Otherwise, we place that queen in that places. If x of k equal to I, so we place that I value in that queen I in that particular place. If k equal to n, then write x of 1 to n. So we already we set down, or we already we placed all the n queens. Now that solution is x of 1 to n. Else n queens again repeating for the remaining places, n queens of k plus 1 to n. So thanks to everyone.
Like, share and subscribe. Hit the bell icon for more updates.